Okay, so we'll start off today with a few of the changes or updates that were made to the slides from last week, where we added a few more examples of real problems. And so I guess this also serves as a quick review of what we covered last week, where we have sort of the distance map, which we'll be using again today. This idea of the thickness map, that you can't do much with the distance itself, and so if you apply this transformation, you can now get much more useful information out of the data. And so that you can calculate a thickness map for the foreground, and that tells you something about the sizes of the objects that you're looking at. You can also do a distance map of the background, and that tells you something about the spaces in between the objects that you're looking at. You can then do sort of the histogram on these things, where you can start to get analyses of sort of what volume fraction is made up with this gap or this size spacing. So here you can see how many objects are of this radius, and here you see how many objects are spaced this far apart. And then some of the things in 3D, which we didn't really have time to cover last week, where here we take an example data set. This is an image of foam where you just see the borders between the bubbles. And so these are slices in the axial direction. These are slices in the sagittal direction. So this is sort of XY, and this is, I think, YZ. And so here you see white is sort of the bubble, and gray or black is the borders between the bubbles. And so we saw this example before in sort of the final screenshot result, and now it's just been added so that you can actually see what steps are required to make it to this. So here we show a 3D mesh of the image because that's a little bit easier to visualize. It's still not super easy, but you can kind of see the boundaries between bubbles in this structure, and this is what's called cellular structure, so that you have all of these sort of regions visible inside it. There are tools in Python for visualizing this quite well. For this, we take a tiny little example out. So this is 20 by 20 by 20 from this image. And we use a library called Plotly, which lets us make interactive 3D graphics so that we can actually look at the structure in a bit more detail and sort of get a better feeling for the bubbles are sort of these gaps in between the plateau borders, in between these structures. And so we can rotate this around. You can do this on much larger images, of course, but then the notebook size gets very, very large. And so downloading a 400 megabyte notebook is not very easy for classes, but this just gives you an idea of what's possible and also sort of the level of rendering quality that you can get out of this. But this is often very useful, particularly when looking at 3D data sets, to get a feeling for what the structures actually look like. So we then make the distance map. So distance transform is a nice tool because it's implemented in n dimensions, and so we can just apply it to this plateau border structure, and now we see almost immediately sort of where the bubbles are. So that when we look at this image, we're able to see that, there's a bubble, 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 based on sort of the local maxima inside of this image. And so it's taken us much closer to sort of the bubble representation we're interested in, rather than just the plateau borders or the boundary structures. So yeah, so this was the example we had showed last week. And this is now running sort of the thickness map creation. This is not the most efficient way to do it, but fundamentally what this does is it goes through all the thickness maps and it fills in the bubbles as we explained last time. So you sort of have this metric of how far away is it from the center, what's the distance, and expand it out. And for everything that's less than that, fill it in. And so for a 3D image that's fairly small, this takes 3 minutes. Obviously for much larger images, it will take much longer. But it now gives us a representation where we actually see the individual bubbles much better, and we can see sort of how round they are. And so most of the bubbles in this sample are nearly perfectly spherical, And so it makes it very easy to see them. This is just a projection of the bubbles that are visible. We can also look at slice-by-slice views of it, where we can see the radius of the bubble in every slice, the same ways we looked at it before. And then we can make sort of interactive views. I think, yeah, unfortunately, this only works. Maybe it works here. Yeah, so there's other tools. This is one called IPyVolume, where you can also make these sort of 3D renderings, and we can make a 3D rendering of the thickness map. And so now we see it's actually already separated most of the bubbles very well for us. We can zoom in, we can zoom out, we can change all of these goofy settings if we're interested. And it gives us sort of a feeling for this. And when you run it outside of a notebook environment, those things look correct. It's just because in sort of the presentation environment, they don't show up correctly. This one. So we covered most of those things already, some surfaces. The last aspect that we added was on the texture analysis. And so so this was where we had this idea of this sort of co-occurrence matrix where we go through the image and we look at points that sort of occur, or intensities that occur close to each other frequently. And so the intensity values are I and j, and the distance away is the delta x and delta y. And as sort of an example for how this could be useful, we added an extra section on sort of how you do this to this brain image. And so we have here an image of the brain. We have the segmentation. We sort of have the overlay. And we see that doing a threshold or sort of any of our standard approaches, except for machine learning ones, don't help us very much in segmenting that object. And so what we can do is we can break the image up into tiles. So here we give each tiles sort of an index, so 0, 1, 2, 3, 4, all of that. So we can group the image up into sort of these regions. This can also be called superpixels, as we've mentioned before. And now we can sort of calculate the texture. And so there's a whole features library inside of scikit-image, which does textures. There's also tools which do much, much more complicated ones, which are referenced in the exercises. And so here, basically the properties we can extract from this are contrast, dissimilarity, homogeneity, energy correlation, ASM. And this goes through each tile and calculates the texture for all of those different values for that entire tile. And so we can run this on the whole image, and then what we see is sort of a tile by tile representation where we have the image itself. We have the region, so how much of it belonged into a region or not, and then the different values for contrast, homogeneity, energy, correlation. And so we can now start to compute these metrics on individual tiles to see if there's anything that distinguishes brain from non-brain. We can get sort of a table out like this where we see all the different parameters, and then we get, we can plot the distributions by doing sort of this pair grid. And this is also one of the exercises where you try to do this with mitochondria in order to find out sort of what textures identify mitochondria and which ones don't. And so this isn't ideal for segmentation, but it can be very helpful for sort of excluding segments that you don't want to keep or segments that aren't of the right region, because you require a segment in order to do this in the first place, which is why we did this grid. So now we'll move on to the topics for today. So this is sort of complex objects and distributions. And so this feeds off a lot of the things that we've covered before, where we have more advanced objects where thickness maps and distance maps alone are not sufficient for doing the analysis that we want to do. So for this, there's quite a few reading materials, if you're interested in learning more about this, we again just cover the very sort of superficial topics here and how you can apply them to specific problems. So the Voronoi tessellations, the self-avoiding nearest neighbors, and two-point correlation things you can feel free to look into if you're interested. We kind of covered this at the beginning already, but we've sort of done sort of all of these steps up until now where we've covered sort of thickness maps, some of the texture analysis, how we deal with complicated shapes, and there's still some issues that we haven't quite solved yet. And so what we're going to do today is talk about sort of what are the motivations for why do we need new tools, what are skeletons and how do you calculate them, what's sort of a watershed segmentation and how does that work and how can you start to break apart separate objects. And then at the end, we'll kind of go to these local and global environment aspects. We'll talk about that later. So really, the learning objectives are kind of how can we extract the topology of a structure. And so I've heard from a few of you already, you're dealing with objects where there is connectivity or you're looking at things like flow, and you want to be able to tell how those objects are linked together and what that topology looks like. How do you identify separate objects when they're connected? And how can we compare sort of shapes of complex objects as they change? So we sort of start off with this example that we had before, where we have these sort of holes in the bone. So these make up cells. And we're able to calculate sort of the threshold, the distance map, the thickness maps as we've done last time, but there's still a lot we haven't really characterized in this sample. And so how can we extract some of those pieces of information? And, if you wanted to know how many cells are alive, maybe the size of the cell or the anisotropy of the cell would tell you something, but maybe there's, living cells are closer together. And so if living cells are closer together, that would be something that would be difficult to assess with the tools that we've developed so far. If we try to look at the raw positions, that doesn't tell us very much. Maybe we could make little boxes and count, but that's also not particularly useful. And so what we really need are better tools for assessing these kinds of problems. How closely packed together are objects? How are they connected to their neighbors? And how can we quantify this in a reasonable way? And what would be great is if we could establish tools that are applicable to a large variety of problems, where it's not just cells, but you can apply it to cells or batteries or a number of other aspects. Another important aspect here is this idea of sort of destructive measurements. And so when you're doing destructive measurements, you can't measure your sample more than once. And so if you look at histology slices from a person, if you take an extract from a person, this tissue is now dead. You can't really analyze it anymore. And so if you want to compare a before and after, it's very difficult to do. You're going to be looking at different parts. You won't be able to track exactly the same cells from one image to another. And so you'll want to have sort of metrics that you can use to quantify the distributions of things that you see rather than the individual points. So the first topic we'll talk about is sort of skeletonization and networks. And there's a data set from EPFL that we'll use for this. It's about sort of tree reconstruction examples. And as you'll see, it's an example that probably, Google obviously has solved quite a while ago, but it's not a particularly easy problem. And so you have sort of this aerial or satellite image, and you want to be able to extract the roads from it. And so this is a different kind of problem than what we've sort of done before. And if we go to, is that the same? Oh, here it is. Kind of our first steps of we have a color image. We can convert it to this Hsv representation, which sort of breaks apart the color and the intensity and the hue, the saturation, and the value, sort of those different representations. That then makes it a lot easier to segment, that we can sort of say the roads are brighter, rather than trying to identify the sort of exact color of a road. We can then perform a segmentation where we say, you know, this is the threshold. All the pixels that are above this we call road. All the pixels that are below are not. And so we can perform this step fairly well. We can even start to improve on this image. So what would you perform after the segmentation if you were trying to extract the roads? Yeah?
You might want to do something like erosion to get rid of rough edges or something like that.
Yeah, so you definitely want to do erosion because you'd want to get rid of all these like scattered points because they're not connected to any part of the road. Any other operations that you perform? You know, we have some big objects here, so erosion might take a long time to get rid of them. You know, this is at least as thick as the road is. Any idea?
Or you could take maybe the biggest connected component.
Yeah, so that's actually what we do. We find out what things are connected together, and we take the largest connected component, and that allows us to throw away all of the things that aren't connected to that. So here we go through and we label the image, and so we now have sort of this image labeled, and you know the road is 1 because it's the largest connected component. Then we have tiny little ones, you know, 19, 31, 29, 18, whatever else that aren't connected to the road. So this gives us a starting point for performing this segmentation or extracting the roads. So we're much closer than we were before. And so if we want to get even further, one of the things that we sort of can apply is this skeletonization approach. And so this is built off of the distance map, where, you know, if you apply a distance map to an object, you can almost start to see what this kind of skeleton would be. I mean, when you look at this, you sort of see the local maxima in these images where, you know, this would be sort of the backbone of the object. And so the skeleton, as we define it here, is sort of the thinnest representation we can have of the object that we're looking at. And so we want basically every point where it's sort of a straight line to just be 1 pixel or 1 pixel long or wide. And everything that's sort of a branch would want to be 3 pixels. And so the idea is to thin away everything that's sort of superfluous, that's not telling us about sort of the specifics of the structure that we're interested in. Yeah?
How do you make it robust so that if for example, it's not the largest component, you can detect that and not select another random component?
Well, so when you do these things, it's very important that you sort of test it on a number of images, and that you probably don't want to have rules in your system if you're building this for a sort of larger study where you say just take the largest component. You should probably have things where if we go back here, skipped a lot. You know, exclude any components that are less than 10% of the size of the biggest component. So that you could say, we want to definitely get rid of all of these objects, but if there were something here that were really big, or for whatever reason, you know, if there's a car on the road, that might split the road in half, but that it would still get that correct. And so you'll probably want or need to have rules that are slightly more complicated than that to get it to work well, but it will depend a lot on your situation. But yeah, it is something you run into, and we'll see, particularly with the skeletonization, that kind of gets very problematic. But so here we have sort of this distance map where we see, you know, our eyes could follow quite easily where this backbone would be by just looking at the values. how would you go about extracting that? I mean, so you can see here fairly clearly what, what you would call the backbone. This point is clearly not on the backbone. This point is. How would you go about separating them? Yeah.
You could do something where you compare around the neighborhood and you only take the max in two directions or something like that.
Yeah. So if you're looking for the local maxima, what did most of you cover in high school? Physics or calculus to find that? If you just took a vertical line out of this, and you were to try to find the local maximum along that line, how would you do that?
Stationary points, zero derivative.
Yep. So you can do the same thing on these images. And so you look at the neighborhood and you perform this sort of gradient operation because it's discrete, it's not a continuous function. And that allows you to find these points. And so what we use here is this idea of the kind of the Laplacian, where you can approximate this operator by sort of this kernel. So, an 8 in the middle and -1, -1, -1 all around. And so you can sort of apply that to the image and then apply some thresholds to it in order to extract the values. And so what you can see here is that you have your sort of distance map there, and you can perform the Laplacian here, and the edges become quite visible, as you'd sort of expect when it goes from this boundary, and that your backbone also becomes quite visible. And so now you can see in sort of the image space what we are trying to calculate or what we're trying to extract. And so we can get much closer to this by just performing a sort of threshold on that value, and we now get this sort of single pixel thick representation. And, obviously this is not satisfactory at all. This is a tiny, simple image. If Google's algorithms were this poor, your navigation system would get lost 20 times going between here and University Hospital Zurich. I mean, there's only one, the image we're looking at is not incredibly complicated. If we go back to the grayscale, this. So it's not a giant city. It's not particularly confusing. There's some houses and a street. And so it's clearly, we're going to need better techniques if we want to be able to reliably extract sort of the roads here. Even the little dashes we see don't really refer to driveways or something, just sort of artifacts from our analysis. And so one of the things we can do with this is called sort of morphological thinning. And so what you can do is get rid of some of the sort of tiny junk elements first, then sort of erode, and then perform the full skeletonization. And so these are the kind of steps that require quite a bit of iteration and experimentation, but that we can take sort of the segmentation we have. We can perform a morphological thinning, which is sort of an erosion, but a slightly safer erosion to perform. We can then perform an opening step, and then perform the the skeletonization operation again, where we sort of create the distance map, and then we look for the ridge in the distance map, and we've improved it massively already. So we've gotten rid of a lot of the extra elements, and it's much closer to being what we're actually trying to extract in these images. So it's still overgrown. And so how would you go about getting rid of some of the last elements? Any ideas? No one. Well, hopefully this isn't the hardest problem you've had to solve before. But I mean, by looking at the skeleton quite easily, we see a lot of the branches that we're not interested in are very short. So we could go and say any branch that's less than a certain length long, we can just remove. We know that that's not a real road. In order to be a real road, it has to be at least 10 pixels long. You know, we're not interested in very tiny short roads. We can also look at sort of the distance at these points and say what's the width. And so if we go back to our distance map we had before, you know, we know there are no roads that are only, you know, 2 pixels wide. We know the smallest road is going to be at least, you know, I mean, if this has an actual unit scale on it, you know, at least 10 meters wide. Anything less than, not 10 meters wide. I don't know, how wide is a road? 10 meters. 6. Anyways, if it's 1 meter wide, it can't be a road because there's no cars that go on a 1 meter wide surface, and that's probably a sidewalk. Yeah?
How do you automatically go through this and find the small branches and get rid of them?
That's what you go to. Yeah. So the actual implementation of that is something that you don't need to, wasn't part of the question. The question was much more of like just visually looking at it, how do you come up with those steps? And so this is where we can now break it down into sort of a more topological representation. And so we can start performing this sort of labeling of our object. And so what we do here is we go through each point and we look at the neighborhood of each point. So the sort of 3 by 3 grid. So this neighborhood idea comes up again. And we try to identify how many points are in its 3 by 3 neighborhood. Because if it's, you know, 1 below, 1 above, and 1 in the middle, that's a segment. That's not a junction of any kind. That's part of a segment. If there's only 1 point in the neighborhood, or 2 points, it's sort of the end or the tip of one of these objects. And if there's more than that, so here, for example, there's 1, 2, 3, we have a junction. Obviously, on this image, it's a little bit difficult to see, which is why we have sort of this extraction here, where we show for each pixel how many objects are sort of in its neighborhood. And so for this one, we have 3, which is 1, 2, 3. For this one, it's 4, because it's 1, 2, 3, 4. And so we can now use this to break down our structure into junctions, which are shown here in white, segments, which are shown in yellow, and sort of tips or ends, which are shown in green. I think we also have a few cases where we have more than 4, and that represents a junction as well, but just a junction where there's, you know, potentially 2 segments coming into it. But that we now can break down our structure into junction segments and tips, which gives us a way to start representing this in a less image format and sort of a more graph-like format. That if we know where the nodes and edges of our graph are, we can represent it in that way. So here we can show it again, where we have sort of all the edges or all the boundaries, where they're equal to 2, all the segments where it's equal to 3, all the junctions where it's equal to 4, and then this one super junction where it's equal to 5. But that basically these are the 3 categories we're concerned with. And if we were trying to get rid of the short segments, how would we do that?
I guess you would start from the 2 points, like the points in class 2, and then travel backwards and see when the first encounter the class 3 or 4.
Yeah.
Probably 4.
Yeah.
And then I threshold cut away all
Yeah, you could do that. I mean, so you could manually implement it where you basically try to traverse along each segment, but it's quite time consuming, particularly if you're dealing with 3D images. This can take a really long time. This is probably not a bad way to do it if you want to make sure your logic works, because when you use image processing operations or operations that someone else wrote, it becomes very difficult to be confident exactly what's going on. And so doing it yourself isn't necessarily a bad idea. But what we can do that makes this task even easier is you can just look at this image here and you can component label it. And then the number of pixels in each component is the length of the segment. And so if you have tiny, for example, this is problematic a little bit here because we see that there's a junction there and a junction there, which means this segment gets counted as a very short segment, and so you might delete it even though it belongs to a much longer segment. And so just doing the component labeling might be too much of an approximation, which is where it can be useful to go from sort of the endpoints or to go from the junctions and kind of grow out and use that way to evaluate it. But as an efficient starting point, you can calculate the component labeled image very quickly and start to do that analysis. And so that once we've broken it down into these representations, it becomes very easy. We can now label every junction. We can label every edge or segment and start to analyze it. So the pruning algorithms, there aren't really ones that work for everything. They're based on a lot of sort of models that need to represent the objects that you're looking at. And so, if you're dealing with street images, there's whole collections of algorithms designed for pruning street images well that know things like streets are straight, they have a certain minimum width, they have a certain style of branching. I guess in Paris, at sort of the Arc de Triomphe, for one of these places, you have this giant roundabout where you have, 7 or 8 roads coming in to one giant roundabout, but typically this is a very rare thing to see, and so you can use a model for roads to say that the topology should not have 14 roads coming into one place. You should only have up to 4 or 5. But this also applies if you're looking at things like bone structure, where you're trying to extract sort of the skeleton of a person, for example, where there's certain lengths of certain bones in certain parts of the body. They're typically very straight, and other sort of analyses that you can perform. And so typically the kind of parameters they have are this idea of the minimum branch length, and this is sort of using the component labeling on the count equals 3, and then the minimum branch width. And so that's the value if you look at that branch and the distance map sort of laid on top of it and try to figure out how big is this width here. And is this branch too narrow to really be an actual branch, and should we remove it? So what we can do here is that we can perform sort of the labeling of the segments. And so here, this is the component labeled image where each color represents a different segment. We can then perform sort of a histogram on this, where we see, there's a number of segments that are less than 10, quite a few in the sort of 10 to 20, and then a few segments that are really, really long. And so this lets us then color them by the length and decide sort of what cutoff might make sense. The color map isn't great here, but if you look at it on your monitor, it's a little bit better, where you can see that sort of these dark blue, certainly anything 5 or less, we can easily remove without changing the topology of the structure at all. So we can now perform these steps. Here we basically just say, we go back. Yeah, we keep all the structures that are longer than 5. So we make an image based on the length and keep everything that's larger than 5. And then we keep the endpoints and we keep the junctions. And so when we combine all 3 of those together, we can now get sort of our skeleton, and then we can compare this to the original skeleton that we're provided. So what's nice with the EPFL data set is we get the ground truth. So we don't have to manually go through and click all of that. We know what the road that was extracted was supposed to be. And so we see we get better than before, but we still have, for example, this problem where there's a gap in that road. And so if you were making a navigation software program, it wouldn't know that you could get from here to here. And so if your topology is not correct, that's hugely problematic. Versus having an extra road that no one will go to is not great, but probably won't cause your entire software to fail at some point.
In this step, is it still, would it be a bad practice, like after all this pipeline, to start opening and closing the image and see if you can gain bigger connected components? It's an operation you don't want to apply necessarily at this stage.
You can. Probably the erosion, they're probably too blunt of instruments to use for these kinds of problems. Because if you look at sort of what would an erosion do to this, it would quite quickly, absolutely destroy everything that it sees. And a dilation would then make this all much thicker. So if you perform a dilation on one of these images, you would see that sort of everything gets thicker, and now you have to go back and sort of thin everything again. And so the sort of operations you typically, so you could perform that earlier, so before you get to this final segmentation. And so this isn't the optimum set of parameters. This was just what I went through to kind of make an example. But you'd ideally want to go back and sort of fix your initial segmentation and fix that post-processing before you go and create this. Once you have this, what you can start to do are sort of link together nodes that are very close. So if you have this representation here, you could say these 2 points, where was it? Oh, this is already back down here. So this was based on the length. These 2 points are very close together. They should be connected. And that would be the kind of rules you try to put in place rather than trying to fix this image. Because basically the whole point of the skeletonization is that you can get away from an image and down to sort of a very compact representation of junctions and segments and nodes where you connect everything together, and you can then have a small file where you save all the roads you have in it. Because even if you look at the data for Google Maps, you could never have all the Google Maps data on your phone. I think you can download it for a city. For Zurich, it's 100 megabytes. But you can have an app on your phone that has all the roads in the United States that's also 100 megabytes. And that's because the images are an incredibly inefficient way to store a topology structure. And if you store it just as this is the name of the object, this is its location, and this is what it's connected to, that's a fairly efficient way to store things. So the other approach we can take with this, which works a little bit better, I think, is we can do the maximum width. And so we can take the segments and look at the distance map for each segment and use that to decide if it's a segment that we should keep or not. So we can then apply that, and we get this sort of topology out. We could also apply both rules at the same time or combinations of the rules, long segments that are not very thick or short segments that are very thick we keep. But that's sort of the spread of how you apply these different techniques in order to get better topologies out. So once you've kind of established this, you can now actually go and try to extract all of those individual points and get things organized in a list format or in a more graph-like format. And so here, if we take all of the points that we have, we can just plot them on top of the image that we had before, where we plot the junctions or superjunctions in sort of purple, the segments in blue, and the endpoints in red. And so that's just plotting each one of the pixels as a point in the image. And so here, it's just going through that entire array based on what neighborhood it is and plotting that in a different color. And so that's not really very interesting. That gives us our first starting point. We can then start to try to actually extract this topology well. And so what we want to be able to figure out is, how can we determine if two nodes are connected, and how can we figure out the length of the object or the length of the connection between them. And so we start off with an image like this, which is sort of what we had before, where you have sort of node, edge, node, edge. You can replace this with junction and segment. This is the sort of graph terminology for this. We can then take the node image, perform component labeling, and we see, this is node 1, this is node 2. We can then take the edge image and perform component labeling, and we see this is edge 1 and edge 2. And that those edge IDs and the node IDs have nothing to do with one another. But once we've done this, we can now select the elements and use dilation to see which edges and which nodes overlap. And so that's using sort of this neighborhood approach where we can take each pixel and say, are there any neighbors in it from another edge or another node in order to process it. And so what this looks like for a real example is that we have this node image here. We then have the node and edge labels here. We then grow the first node, and we see that it found edge 1. We can then grow the second node and see that it found edge 1 and 2. And so that lets us now establish that this node is connected to edge 1 and 2, and this node is connected to just edge 1. We can do that on the whole image. And we can now establish sort of what's the connectivity of all the different objects that we're looking at. And so here we see edge 1 connects points 1 and 3, edge 2 connects 2 and 3, and we can start to make what you have in sort of graph theory is like this connectivity matrix, where we can see all the nodes on sort of the x and the y axis. And this shows us if they're connected or not. So if it's non-zero, they're connected. And the intensity is the length of the connection between them. And so this gives us sort of an easy way to represent the topology of the structure in a sort of single matrix. We can also then plot it in the same way we did before, where we show the nodes and then we plot the lines that would directly be connecting them. Once we've done this, it makes it easier to calculate things like tortuosity, where, how direct is the path between 2 points, where we can see, this would be the straight line distance. And if we go back here, we see this is the actual arc length. And so the straight line distance is much directer than the actual arc length of our image. And so we can start to quantify that by measuring sort of the ratio between this length and the arc length. And this can be very helpful for assessing other properties of a system. And so in geology, it's very useful for sort of diffusion and fluid transport, that if you have structures that are very direct, this happens very quickly. And if you have structures that are very high tortuosity, then it does not happen very quickly because there are sort of lots of twists and turns something has to take. For analytical chemistry, it's quite useful in tasks like chromatography, where sort of the longer routes take more time. And in vascular tissue, it's a sign of pathology. And so if you have a lot of blood vessels that don't flow very directly or don't go directly to where they're supposed to go, that can be a bad sign. And so it's a metric that we can extract once we've established this kind of graph representation for what we're looking at. So we can now do this for the image that we have and show for each node by sort of how transparent it is, the level of tortuosity. And so the very high ones are the ones that appear very dark, and the very low ones are the ones that don't appear very dark. And so for a roadmap, this isn't particularly interesting. We basically just see the very tiny short segments of very low tortuosity. compared to the other ones. So we can then perform sort of this full graph analysis. And so once you've organized objects as nodes and edges, you can use toolboxes in R or KNIME or Python to represent them with sort of graph structures. And so here we use this library called Network X, where you add all of the nodes and add all of the edges. And now you can see sort of what the graph representation of the structure you have looks like, where you see the name of the node and the color indicates sort of how wide it is at that point. You can then plot that on top of the image that you had before to see that. And the advantage of putting it in this sort of Network X representation is that you can now perform all kinds of analyses on the graph itself. And so here we just show something about sort of the connectivity or the degrees, where we calculate the degree of each point and we can see how many different things each node is connected to. And then a majority are sort of these straight line, but there's a few nodes that are connected to a number of different objects. And so these nodes, if you were looking at the map of a city, would be places where maybe traffic jams are most likely to occur, or where connections are most important. But that you have sort of the ability to easily extract a lot of these metrics once you've put it into this sort of graph-like structure. So are there any questions on that? If not, I think we'll take a short break before going to the watershed parts. Okay.